All right. Are you ready to get started?
Yeah, I was finishing up number 9.
I haven't finished D or E, so we can finish that one together.
Okay.
I haven't finished.
I was working on D, and then all I have is E after that.
Okay.
So we'll
And then-
figure it out.
All right. Sounds good. So for number 1, I said that heat transfer moves into a system like the heat enters an alcohol thermometer and changes the volume inside so that the alcohol goes up or down. What did you use for heat transfer?
I use soup. So like you have stove and the pot or container.
Yeah.
The heat transfers to the pot.
Okay, for work, I said that'd be like pumping air into a tire because like it's more than what would normally be in there, so you have to use force to get it in. I don't know.
Which makes sense. Um, I I've stuck with the soup thing the whole thing.
That was probably smart. What did you do for your internal energy then?
Because the internal energy is stored within the container,
Uh-huh.
and um, so as the soup is boiling, you have the heat transferring to the container, and
Yeah.
then the container does the work on the soup, so it evaporates the water, but the heat stays with the container as like an equilibrium source.
Okay, that makes sense.
So that's what I used.
Okay, so for number 2, I use the equation delta U equals Q minus W. And so I did the 3.0 times 10 to the 6th minus the 8.0 times 10 to the 6th. And then from that number, I subtracted the 4.5 times 10 to the 5th, which gave me negative 5.45 times 10 to the 6th joules.
That's what I got. Uh, do we need the negative or
I don't know.
because that seems just more like a directional thing,
Yeah, because
doesn't
I
it?
kept the negative just because like that was the like numerical value ended up being negative, but I'm not sure if you need to keep it or not. I
Okay.
don't I don't think you need it, do you? I mean
I
what you
don't
know
know.
is that it's like a directional cue.
Yeah, that's what I thought of it because if you're adding force one way or another,
Yeah.
that's when you could add the positive. So
Yeah.
I don't know. Both ways work, I would say.
Yeah. Okay. What did you do for number 3?
So for number 3, the work is equal to the area of the path.
Mm-hmm.
And so I found the area of the triangle since that's all we need.
Yeah, that's what I did as well.
So I got 2.4 times 10 to the third joules for the area of ABDA.
Mm-hmm.
And then I explained because the area is less in ABDA than the area of ABCDA, the work done by the path of ABDA is less than the work done by the path ABCDA.
Yeah, that's what I got as well.
Sweet. Hello, Dago.
She's being a clinger today. She won't leave it alone. I don't know what she's going on
She's cute.
about. Thanks. She's my baby.
Oh.
I know, I like her a lot. Okay, for 4A, so the equation for efficiency. This is why I normally lock her out of the room I'm in. So the equation for efficiency is W over Q, but then the W is also equal to QH minus QC. So then I have 1 minus QH minus QC over QH, and then you can just cancel it out. So it's 1 minus QC over QH. And so I have 1 minus 75 over 95 kilojoules, which gave me 0.2105. And then for W, to get the work done, I used the original equation, which was the efficiency equals W over Q. So I multiplied the efficiency by the QH. So the 0.2105 by the 100 kilojoules they gave us, and that gave me 21.1 kilojoules of work.
That's what I got.
Okay, how did you, or what did you say for number 5? This one I don't know if I did it right, but it makes sense. Like I had to like look it up online.
Yeah. I looked it up too so I could figure out how to word it.
Yeah.
It just felt messy. But so what I said is by using the best materials that provide the best insulation to a system, all components can be isolated and the heat transfer to the environment is reduced. But heat transfer cannot be reduced entirely because there is always heat flow between the system and its surroundings.
Okay, so that's kind of what I said. I said no ooh, that was not English. No, engines transfer heat between regions to make mechanical energy. If there's no heat transfer, the heat engine won't work. But I like what you said, where like you can isolate it so it reduces it, but there's still going to be heat transfer.
Right.
Okay.
Either one works, honestly.
But I think yours is like, I like yours better, so we're gonna use your number 5 because I didn't
Okay.
like isolating him because I was like, it has to happen. So suck it up.
Suck it up. Suck it
Um,
up. Nice.
for number 6, I said no. If you leave the refrigerator door open, more energy will be needed to cool the new system because now it's including the entire room instead of just the fridge. And I said there will be greater energy needed, so more heat will be produced by the system to like try to counteract that heat to bring it back down. So you'll actually end up releasing more heat into the system than you are cooling the system. So like if you put
Oh.
the coils or whatever they are, if you put them in like a separate room or like isolated somewhere, then it would get colder. But since they're not isolated, then you won't be getting any colder.
I like that. That's really good. All I said was the the fridge will try to include the whole room as the system,
Mhm.
but the heat taken will be released, so there won't be any differences in temperature.
I read that somewhere else too, but then I also read this one, but that one I read and that was the one that like made the most sense to me. And that one I
Yours
like,
yours is like detailed to the point.
we'll use my number 6. I'll put a circle.
Okay.
All right. For 7, I have the coefficient of performance is equal to QH over W, which is QH minus QC. So I have QH over QH minus QC. So that gave me negative 20 plus 273 to convert it to Kelvin, divided
Yeah.
by negative 20 plus 273 minus 50 plus 273. And that ended up giving me negative 3.61. But I don't know if that's right because I feel like all the coefficients we've used so far have been like a
Positive.
1%, or like they're like a number between 0 and 1. So I'm not even sure that I did that one right.
Well, I rearranged mine. So instead of subtracting by the 50 plus 273, it's subtracted by the negative 20 plus 273. So I had 253.15, if you want to do that, divided by 70. Instead of having a negative on the bottom, I had a positive. But I still got the
Yeah, it's still the
3.61.
same number. I guess it's the same then. The only thing that confuses me is I thought when we like the coefficient of like friction and all that we did, it was like almost always a number between like 1 and 0. I feel like maybe I'm imagining that.
No, it's true. There was one time I was getting a number above 1 and it wasn't working. So I decided to look up if it's possible. And it is.
Oh, okay. Well then I think we did it right. I don't know if it's supposed to be negative or positive though.
I
But
think that's a directional thing
yeah, I
again.
think so too.
So
I don't like about physics. I'm like, is it right or is it wrong?
I know one tells you.
I know. Last week on on the individual exercises, there were two problems that like I couldn't get right, and I was like, I know I'm doing this right. Like I knew I had the right like equations I was using because it was the same stuff we did in lab. And so finally, I was like, I emailed him, and he's like, "Oh, you're close. Just like he was like, oh, use all of these random numbers." And so I tried that. That didn't work. And then I went to like the class meeting, and while I was sitting there, I'm like, oh, just for kicks and giggles, I'll put all the temperatures in Kelvin. And then it was right. I was like, dude, you could have just told me to use Kelvin. Like I spent 3 days on this.
Dang.
I was mad.
There were a couple. I don't even know how I got them right.
Yeah.
Honestly, it's like convert, or I ended up having to go use online.
A lot of them,
Like go.
I was like, okay, well, this temperature didn't work. So like one of them was like the weirdest thing where like I converted all of it to Celsius and I solved it and then tried to put it in Celsius and it didn't work. So I converted them all to Kelvin and that didn't work. And so like I got the final temperature in Kelvin. I was like, well, I wonder what it'll be if I convert it to Celsius. And then I tried it that way and it worked. It's just stupid.
Huh.
Right?
That sounds like a headache.
Yeah, I didn't really like it. But like last week was slow for me at work, so I had time. It was fine.
At least you had time, right?
Yeah. All right. How did you do number 8?
So number 8, I found the average temperature of the two first and converted it over to Kelvin. And then I took the heat transfer and divided it by that average number.
Mm-hmm.
So the 35 plus 45 divided by 2, you get 40 degrees Kelvin. 40 degrees Celsius. And then you convert it over so you get 313 Kelvin.
Yeah.
And then you take 4 by 10 to the 6 divided by the
temperature.
The temperature. And I got 1.28 times 10 to the 4th joules over Kelvin.
That's what I got as well. All right, for number 8 on 9, so I used the equation we used last week, which was the Q equals MC delta T.
Yeah.
Well, I used the 20 kg, the coefficient of the water, or whatever that one was called, the 4,186. And then this part I was confused. I wasn't sure if we were doing the 90 minus 10 or the 50 minus 10, but I did 50 minus 10, just because that seemed like a nicer number. And that gave me 3.35 times 10 to the 6th joules.
Oh, it's temperature initial minus final.
I know, but there's 2 initial ones. Like, are you using the temperature of the 90-degree water that you placed in the 10-degree water? Or are you using the temperature of the 10-degree water that had 90-degree water added to it? You know? Because I ended up just doing the 50 minus 10. Did you use a different one?
Well, when I was looking at it, I was thinking about the 90 as the initial, because the 10 is the other thing you mix it with.
I know.
So
I know, but that's what I'm confused about, because you could also say, well, you're starting with the 10 and you're adding the 90. So I didn't know which one to use. But I feel
did 40.
that messes up all the numbers if you don't use that one. You know what I mean?
That you have a valid point. I do believe it's the 40, like you said, the 40-degree difference.
Okay.
Because that's what I went with as well.
Okay. As long as somebody else did it too. Because I was like, I have no idea which one he wants this. Because it's not like he's like, tell us the heat transfer for this specific thing. Because they're both water, so it doesn't help.
Good point.
Anyways, for the efficiency, I use the same equation or for part B, I used the same equation that we used before, which was the efficiency equals QH minus QC divided by QH. So I ended up with the 90 plus 273 to convert it to Kelvin, minus 10 plus 273, and then I divided it by the 90 plus 273, which gave me 0.2203.
I got
And
that.
then to find the work, I multiplied that number by the number I got in A, which was a 3.35 times 10 to the 6th. And then that gave me the final work as being 7.38 times 10 to the 5th joules.
That's what I got.
Okay, how did you do number C?
So C, so we have I might have used different letters than you, but so I have the delta S total equals delta S hot plus delta S cold.
Yeah.
Converted that to the transfer of heat cold over the temperature cold minus the heat transfer hot over temperature hot. And then I separated the two so I could find them. So the change of hot, the heat transfer over the TH,
Mhm.
I use the what you found in A over 273 plus 90, which equals negative QH over TH. So it comes out to be negative 9.225 times 10 to the third joules over Kelvin. And then for the cold, uh, the bottom changes to
The 10 plus 272?
plus 10 equal. So it comes out as 1.183 times 10 to the fourth joules per Kelvin. And then I went back to the original equation. You add the two together, and I got 1.96 times 10 to the third joules per Kelvin.
Yeah, that's what I got as well. Yeah.
A little lengthy, but
I know. It's a lot of steps, but they're not hard steps, luckily, but there's still a lot of steps. And
you
then,
just miss one little
yeah, and then it's like game over.
yeah.
All right, so let's try with
So I had solved D,
okay.
but the part that I didn't get to is so compare it with the work done by the Carnot engine.
Uh,
And I was trying to look things up to hurry through, and someone said it was about a 75% um, difference of work.
so would you?
But
I think what you is you'd find the work that you did, and then compare it with the work that we found in part B. So don't you do like the final minus initial divided by the final, and then multiply it by 100? Isn't that how you do it? Would that give you the right number? Maybe it's the other way.
okay, I'm back.
Hello.
I don't know what happened.
It's okay. I didn't realize you were gone, so that's fine.
Oh, okay.
I was just trying to. I'm just trying to plug in numbers to see what I can get that's close to 75%.
I end up with some when I divide the two together, I get 0.0075. Even timesing that by 100, that's only 0.75%.
So how did you get the work, the unavailable work?
So the unavailable work is the total of what we found in C, so the 1.96 times 10 to the third, times the temperature cold in Kelvin, which is the 283.15.
Yeah.
And that gives you your unavailable work.
Okay. So that gives.
Oh, I think I see. Instead of doing the bigger number on the bottom, try the smaller number on the bottom.
So that number was like 5.55 times 10 to the fifth.
Third.
Oh, you got yours to the third?
Yeah, because you have the 1.96 times 10 to the third. Let me check that.
Or 283.
Yeah.
1, 2, 3, 4. I'm getting to the fifth.
That would explain a lot.
That would explain why yours is 7.5 instead of 75 if you were using the number. Okay, so then I think we got it. Did you have that written down that we can use yours?
I have it written down. I just need to do the 5.55 times 10 to the fifth over the 7.38 times 10 to the fifth, which equals 75%. And so the Carnet, not the Carnet engine does 75% more work than the other engine.
Yeah.
Writing that down.
And then I think I have the answer for E, but I'm not sure. You might want to fact check me.
All right. So E, discuss how everyday processes make increasingly more energy unavailable to do work, as implied by this problem. Okay. What do you think?
My guess is this problem is a perfect scenario situation. But in reality, it's not going to be a perfect scenario. You're going to lose energy. So you'll have even more work unavailable than what you already have unavailable because you're losing energy and it's not a perfectly closed system, is my guess. That's my only guess.
Well, it sounds reasonable.
Right? I'm that's the only thing that makes sense to me without being a mechanical engineer.
And you would be absolutely right. I've done a few things with automotive and welding. You lose a lot.
Yeah, so I think what we can say is not every system is 100% efficient. And so if you are any less efficient than the system we have here, then you're going to have even more work unavailable, I think is what we'll say for E. Can you write that down so we can put it with your number 9?
Yes. Percent.
Hey. Girls.
Every system works at 100% efficiency. Therefore, there will be even more work unavailable.
Yeah. Because it's asking how do every processes make increasingly more work unavailable? So I think that makes sense. I think we've answered the question.
All systems. So not every system works at 100% efficiency. Therefore, there will be more work unavailable in all systems.
Yeah, that sounds good to me.
Okay.
Okay, so you are going to send number 9. Do you want to send, since we like your answer for number 5, I could do the first page, and then you can send me a picture of number 4 and 5, and I can do 6, 7, and then you can send a picture of 8 and 9. Does that sound good?
That sounds perfectly fine. So 4 and 5 on mine, as well as the last page, and you get first page and the last 2 on the second.
Yep.